All right, assalamu alaikum everyone. We are starting. So today we're starting our next topic, which is trigonometry. We're starting our next topic today, which is trigonometry. So we're done with binomial expansion and quadratics until now. The next few topics are going to be in this order. We are doing trigonometry right now. The next is going to be coordinate geometry, except equation of circle, and then we do differentiation and integration. All right, so that's the order that we're going to be following for the next few topics now. We're doing trigonometry, and then we do coordinate geometry, differentiation, integration. Okay, that's what we will be doing. And then hopefully after that, we will have first functions and then circular measure, equation of circle, and ABGB. All right, but we'll decide the order for that later. For now, the next four topics are going to be like this: trigonometry. We're starting that today. Next is coordinate geometry, then differentiation, and then integration. Okay. I said something else earlier in the beginning, but I realized later that we would not be able to have a sync. We'll not be able to sync this with paper 3 otherwise, because I need to start differentiation and integration soon in my P3 course, and then there are a couple of you who are taking both P1 and P3. So if you don't know P1 differentiation, integration, or trigonometry, then you can't understand P3 differentiation, integration, and trigonometry. So that's why I need to do these topics first, and then we will be doing the other topics which are not as relevant for paper 3 later. Okay. So let's start with trigonometry today. So there are some concepts of trigonometry that you already know from O levels. Okay, but there are only some. We are quickly going to review those in the first few minutes, and then we extend those ideas to what we have here in A levels, as in some extension of that. We'll be extending that, extending the idea of sine, cos, and tan functions to basically bigger angles. But let's just jump into it right now and see what is to come. So remember what three functions you used to have in O levels. You had a sine function, sine theta, then you had cos, and you had tan. How did you used to define these functions? Sine was defined as opposite over hypotenuse, right? That was one way to define that. Some people call this perpendicular over hypotenuse. That's
अच्छा मैं
also
पढ़ने
fine.
लगी हूँ पढ़ने लगी हूँ भाई
Okay, thank you, Maheen, for that information. Okay, sine theta is opposite over hypotenuse or perpendicular over hypotenuse, and cos theta is adjacent over hypotenuse or base over hypotenuse. And tan is defined as opposite over adjacent, or you could say this is perpendicular over the base, right? That these are the definitions that you have learned for sine, cos, and tan, right? And there are different ways of remembering this. One was some people have curly brown hair through proper brushing. For this perpendicular hypotenuse and base over hypotenuse and perpendicular base definitions. And there are other ways to remember this as well, but you know that from O levels already. This is how these functions were defined. Okay. Now, these were defined using right angle triangles because hypotenuse is only defined for right angle triangles. That's not there in any other triangle, right? Hypotenuse is the side that is opposite to the right angle. So that's only for right angle triangles. So let me draw a right angle triangle here. And see how these definitions connect with this right angle triangle. So we have this triangle. Let's say this angle here is 90 degrees. The side that is opposite to 90 degrees, that is the hypotenuse. And this angle is going to be alpha, and this angle is going to be beta. Let's say we call this angle alpha, and then we call this angle beta. Now, this is the hypotenuse. But what about perpendicular and base? Perpendicular and base are basically defined with respect to alpha and beta, with respect to the angle. So if you were finding, for instance, sine of alpha, what would be the perpendicular? The perpendicular would be the side that is opposite to this, right? We can name these sides like this. We could say this side is maybe A, this is B, and this is C. Sine alpha would be B over C. But if we had to find sine of beta, what would that be? The side opposite to beta is A, and the hypotenuse is C. So that becomes A over C. All right. So sine alpha would be B over C, and then sine beta would be A over C. Okay. Then what about cos? Cos alpha would be the side that's adjacent, which is A, over the hypotenuse, that's C. And cos beta would be adjacent over hypotenuse again, but with respect to beta, the side adjacent is this. The base would be B in this case. So this is going to be B over C. And then similarly for tan, we have tan alpha equals opposite over adjacent, the perpendicular over base. With respect to alpha, this is perpendicular, and this is the base. So that's going to be B over A. And for beta, tan would be A over B, right? So these definitions of opposite and adjacent, or you could say perpendicular and base, they are basically coming from what angle you're talking, which angle you're talking about. So the side that is opposite to the angle that you're talking about, that's perpendicular. And the side that's adjacent to the angle that you're talking about, that's the base. Hypotenuse remains the same because that's always the side that is opposite to the right angle. Okay, so now this is one thing that's important, that you need to understand the basic definition of sine, cos, and tan that you've done in O-levels already, how they're defined with respect to which angle you're using. Okay, this is for right angle triangles. The definitions come from this right angle triangle. But when you do not have a right angle triangle, there were some other rules that you used to use. For instance, if I have a triangle like this, and it's not a right angle triangle, it's not even isosceles, let me just change this slightly. So it's a general triangle now, okay? This is the triangle that we have. Now, let's say this side is, this vertex is A, this is B, and this is C. The side opposite to A, we would call that small a. The side opposite to B, we would be calling that small b. And the side opposite to C, we would be calling that small c. All right. Now, if it's not a right angle triangle, we have two rules that are defined here, which are going to be sine rule, which looks like this: sine of A over A, that is equal to sine of B divided by B, and that's equal to sine of C divided by C. This is one rule that you need to know about. Sometimes you have to use this. When do you use this rule? When you don't have a right angle triangle, okay? Now remember how we used to use this tool? You basically need a pair of side and angle. So sometimes what happens is you're given maybe this side is, let's say 4, and you have this angle, maybe this angle is 30, and you have, let's say this angle as well, this is 45 degrees. And then if you want to find, for instance, this side C, you can use this pair and this pair to find whatever is the unknown. So you need one pair of angle and side given, and then one other piece of information in the triangle, and you can use sine rule to find any missing information. So this is another thing that you know from O-levels. You need to know this. And then there was another rule which you normally use when you don't have a pair of side angle given, like side and angle given like this, and that is called cosine rule. That looks like this: a square plus b, a square equals b square plus c square minus 2bc cos of a. All right, when do you use this? Generally, we use this when we don't have a pair of side and angle. Instead, we could have something like this given. For instance, we could have this side and maybe this side, and the angle between them. If these three things were given, it's called the included angle. If you have two sides given and the included angle given, and you have to find, for instance, this third side, you could use this formula for this, right? Or you have all the three sides given and you need to find some angle, then also you could use this formula. Now, what's important to remember about this formula is the side that you have on the left side of this formula, A, this angle here is of the vertex that is opposite to that side. So for example, if this side is A, that means this side, the angle that you're taking cos of here should be this side, should be this of this vertex, right? Then you can use this cosine rule. So these are some concepts that you have done in O-levels and you still need to know them. Okay, that's the first thing. All right. How sine, cos, and tan are defined for right angle triangles. That's the first thing that you need to know about. Then if it's not a right angle triangle, you need to know how to use the sine rule and cosine rule. You need to sometimes use these in some problems. We will basically have some mensuration questions sometimes in which you will need to use these. In a later topic, circular measure as well, you will have some triangles, we'll have to use trigonometry. So you have to keep these in mind. These are the concepts that you've done in O-levels already, okay? Now, apart from this, most of the stuff is going to be new for you. So what's the first new thing that you need to know about? There is another unit of angle that exists. So we are used to talking about degrees. We will be talking about this in a bit more detail in circular measure later as well, when we do questions related to radians. But let me just explain it to you right now, what a radian is, because we need that in this topic as well. And we haven't done circular measure yet. Let me just quickly explain radian as an angle unit. Radian as an angle unit. Okay, now what is this about? So remember, one unit that you use for angle is degrees. So if you have a circle like this, what would be the total angle of the circle? It's 360 degrees. What does 1 degree mean here? 1 degree would be, if you were to divide this circle into 360 parts, each part would have an angle of 1 degree. So in degrees, we would say the total angle of a circle is 360 degrees, right? Complete angle. We have another unit for angle now. And how is that defined? You also need to understand this definition of radians. It's defined like this, that if you have a sector of a circle like this, if you have a sector of a circle like this, such that the arc length of this sector, is equal to the radius of the sector. If the arc length of the sector is equal to the radius of the sector, like this, if the radius was 3, let's say, then if the arc length is also 3, you have a sector like this in which the radius is the same as the arc length, the angle that you get here is 1 radian. Okay, that's the definition of radian. What's degrees? If you were to divide a circle into 360 equal parts, each part in those 360 parts would have an angle of 1 degree. What about radians? Radians is when you divide a circle like this in sectors such that a sector has an arc length that is equal to the radius of that sector, the angle that you get here is 1 radian. Okay, this angle is 1 radian. Now, what does that mean? Let me write that down here. Arc length of this sector. What's this? We're saying this arc length is r. What's the angle that we're getting in radians? The angle that we're getting in radians for an arc length of r is 1 radian, right? What's the arc length of a complete circle? That would be the circumference, right? Arc length of a complete circle is called circumference. What's that? It's 2 pi r. Circumference of a circle is 2 pi r. So when arc length is 2 pi r, what's the angle of the whole circle? If we multiply r by 2 pi, we get 2 pi r. So we multiply 1 by 2 pi as well, we get 2 pi. What we understand from that is, in a complete circle, the angle is 2 pi. So 360 degrees corresponds to 2 pi radians. That's the important thing that you need to remember. Okay, 360 degrees, that corresponds to 2 pi radians. So a whole circle in degrees is 360 degrees, and a whole circle in radians is 2 pi radians. Okay. Now, how do you convert between degrees and radians? You can just use simple ratios now once you know that 360 degrees corresponds to 2 pi radians. If I have, for instance, some angle written in degrees, I could write the same angle in radian as well, which is just another unit that we have for angle now that we need to know about. In degrees, if we have 360 degrees, we just talked about this, that this is going to be 2 pi in radians. Okay, pi is just a number here, just like 3.142, right? Pi is just a number. Okay, you can write it in decimals as well. That will be 2 into 3.142. That's like 6.28 something. That's the value that you have here, but the exact value is 2 pi. Okay, it's not necessary for you to write it in pi in terms of pi every time, but when you need an exact value, you can write it like this. Or if you don't need the exact value, you can write it like this as well. Okay, so it's actually 6.28 something. 360 degrees corresponds to 2 pi radians. Now, what if you had 180 degrees? What would that correspond to? 180 degrees, if 360 degrees is 2 pi, 180 is half of 360. What's half of 2 pi? Half of 2 pi would be pi. And then what about 90 degrees? 90 degrees is 1/4 of 360. So what about radians? Divide 2 pi by 4. What do you get? You get pi over 4. In fact, this is not pi over 4, it's pi over 2. This is easier to use. So this thing, 180 degrees and pi radians, this is a good conversion ratio that you can kind of remember. 180 degrees corresponds to pi radians. And this is what you can always use for conversions. So 180, for instance, just corresponds to pi radians. What about 90 degrees? 90 degrees is half of 180. So it becomes pi over 2. If you had, for instance, 45 degrees, 45 degrees is 1/4 of 180. So this becomes pi over 4. 60 degrees is 1/3 of 180. So this becomes pi over 3. 30 degrees is 1/6 of 180. So this would become pi over 6. 0 degrees is just 0 because 0 degrees in another unit would also be just 0. So this is another unit that we have for angles now. We are used to using degrees. That is also an important angle unit, but a lot of times we would now be using radian. And this is how you convert between degrees and radians. You can use ratios. 180 degrees corresponds to pi radian. That's the conversion rate that you can use. So now if I had not one of these common angles, because in this case, it was a direct multiple, 180 was basically a multiple of all of these angles. So it was easy to figure out how to write down those numbers in terms of radians. But what if you had a different angle? For example, if it was, I don't know, 140 degrees, how would you convert it to radians? That's the question. And if you had something in radians, how would you convert it to degrees? This is the ratio that you can use. So if you want to convert 140 degrees to radians, you can say, we don't know what that value is going to be. We know that degrees is 140 degrees. And in radians, we have to find what it is. Now, using that ratio, 180 degrees corresponds to pi. You can figure out what the value of x is going to be. Now how did you used to do it? You could just multiply diagonally like this. You could say this gives you 140 pi, right? That equals 180x. And the value of x turns out to be 140 over 180 times pi. And that gives you 14 over 18, which is 7 over 9 pi. So if you have to convert between degrees and radians, all you have to do is just use ratios like this, and you would get a result. Now you can generalize this as well and kind of remember a formula to do this directly. If you have to go from degrees to radians, you can actually use something like this. You can say degrees to radians. For this, what you can do is, whatever the number is, you multiply that number by pi over 180. So if you have a number in degrees, you want to convert it to radians, you multiply that by pi over 180. And if you want to convert from radians to degrees, what you do in this case is, whatever the number is, you multiply that by 180 degrees over pi. That's the conversion method that you can use. Okay, so you either have to multiply by pi over 180, or you have to multiply by 180 over pi. You have to do one of these two things. Either multiply by 180 over pi, or multiply by pi over 180. So in order to convert from degrees to radians, you do this. In order to convert from radians to degrees, you do this. Okay, and these are some common conversions that you need to memorize, that you need to remember. Now, you will tend to remember this after you're done with some practice. So it's not like you have to just, try to rote learn this. That's not how it works. You will just do a lot of practice and start remembering this. 180 degrees is pi radians. 180 over 2 gives you 90 degrees. That corresponds to pi over 2. And similarly, the rest of them. Okay, so these are some common angles in degrees and their corresponding values in radians. Okay. Now, once we know that these are the conversions between degrees and radians and degrees, we can now try some examples. If we had, for instance, 180 degrees, or in fact, if we had 157 degrees, how would that convert to radians? It'll be 157 into pi over 180. Okay, and you can see what that turns out to be. 157 into pi divided by 180, that turns out to be 2.74 radians. And if we had to convert, for instance, pi over, or maybe 2 pi over 5 radian to degrees, what would you do? 2 pi over 5, multiply that by 180 over pi, and that will give you something like this. This is 72 degrees. So that's how this conversion works, okay, between degrees and radians and degrees. Does that make sense to everyone? The conversion between degrees and radians, radian degrees. Any problem with that?
No, sir.
No? Okay. So I'm just thinking, I've spent quite some time on this, and if we start trigonometry now, we would not be able to achieve much in the rest of the time that we have. So what we could do instead is, we could actually, since we're talking about radians, and we have discussed this basic trigonometry as well, let me just complete the concepts of circular measure today, okay? I might explain that to you in a minute. What I'm going to do is, instead of trigonometry, because we actually have only 30 minutes left, and we would not be able to do an important concept of trigonometry today. What I'm going to do instead is, I'm going to just complete circular measure today. It's a very small topic. This is a major part of this. This is a significant part of this topic, as in conversion from degrees to radians, not a major part. It's a significant part of this topic, understanding and working with radians. But once you're done with this, the rest of the concepts are actually pretty straightforward. So what we're going to do instead today is, we will actually complete the concepts of circular measures. So we can get done with this, and then you have something to do for the next 2 days. If we do trigonometry, we would actually not have something substantial done by the end of today's class, and then the next 2 days would kind of be wasted for you guys, as we would not have much to work on. So what I'm going to do, I'm going to do is, I'm going to discuss circular measure, okay? Now, that should not confuse you, because for circular measure as well, we need all of these concepts that we've done. Basic trigonometry from O-levels, this was kind of a revision of what we've done, what you have done in O-levels. This is something that you need to know about for circular measure as well. And understanding radians, this is also something that you need to know about. So what is a radian? Let me repeat. Radian is another angle unit. And what is this about? If you have a sector in which the arc length is the same as the radius of a sector, the angle here is going to be 1 radian, okay? Now, what that means is, in a complete circle, you're going to have 2 pi radians. So 180 degrees corresponds to, 360 degrees corresponds to 2 pi radians. And then from that, we get that 180 degrees corresponds to pi radian. And then you can do all of this conversion like this. Now, for this conversion, it does not matter if your calculator is in radian mode or degrees mode. That's irrelevant, because these are just numbers that you're multiplying. You can multiply numbers in any mode. This conversion is not going to be effective. Radian mode and degrees mode on your calculator, Ima, that is going to be relevant when you have angles inside sine or cos or tan. When that happens, then that mode is important. Okay, we'll talk about that in a few minutes now. Okay, for now, that's not important. You can multiply numbers in degrees or in degree mode or radian mode. It does not make any difference. Okay, you're going to get the same result in any of those modes for these calculations. For these calculations, it doesn't matter what mode your calculator is in. Okay. All right, so we understand this conversion, right, between degrees and radians and radians and degrees. Now, since we are talking about circular measure now, what do we need to know for this topic, circular measure? So if you look at the syllabus, circular measure basically just has the same concepts that you've done in O-levels related to areas and perimeters in a circular shape. So area of a sector, perimeter of a sector, arc length of a sector, perimeter of circumference of a circle, all of those concepts that you've done in O-levels, they are part of this topic, circular measure, in your syllabus. The only difference is that you would be doing all of these calculations in radians instead of degrees. Okay, so you need to know about area of a sector, perimeter of a sector, arc length of a sector, and areas of triangles will be needed sometimes as well. All of those you've done in O levels already, but in O levels you're used to doing all of that in degrees. Now we will just be doing all of those calculations in radians instead, right? That's the only difference that we have. Now, once we understand this conversion between radians and degrees and radians, and we understand that radian is a new angle unit that we have, now let's talk about areas of sectors that you have done in O levels. Remember what the area of a sector was given by, and what the arc length of a sector was given by. You can write both of them here: area of a sector and arc length of a sector, or just arc length. Do you remember what the formulas for these two were? Theta over 300 and 360 into 2 pi r. That's what you used to do for arc length, theta over 360 into 2 pi r. And what about area of sector? What was the formula for that? You used to have theta over 360 multiplied by pi r squared. Right? These were two formulas that you have done in O levels related to arc length of a sector and area of a sector. Now, where do these formulas come from? What are we trying to do with 2 pi r here? Remember, 2 pi r is the circumference of the whole circle. So if you had a circle like this, what would be the complete arc length? This complete arc length of a circle would be 2 pi r. And if we were to carve out a sector from the circle like this, that we have the center here, and then we say we have a sector like this inside the circle, and we only want to find this arc length. How do you find this arc length? You say, okay, let's say this angle is theta. The angle of this sector is theta. What's the total angle of the circle? The total angle of the circle is 360 degrees. All you used to do was you said the complete arc length of the circle is 2 pi r. If we just find the ratio of that, the proportion of that falls in this sector, that proportion would be theta over 360. For the complete circle is 360 degrees, but for this sector, it's theta. So if we were just looking for this arc length, we would say, let's find the proportion of 2 pi r that falls in this sector, and that will be theta over 360 multiplied by 2 pi r. That's what you used to do in O levels, right? But now we're saying, instead of working with degrees, we are going to be working with radians, all right? How do we convert this formula to radians now? Let's use the same thing as we're doing here. What's the circumference of a circle? Complete arc length of a circle, that's 2 pi r. But now we say that the angle is in radians instead. Remember, in this formula that I wrote above, theta was in degrees. But now, in the problems that we do here, the angle is going to be given in radians instead. So if this angle theta is in radians, what is the formula going to change to? The total angle of the circle, instead of being 360 degrees, we would say that angle is 2 pi instead. Okay, so instead of theta over 360, now we would have theta over 2 pi. And now if we were to simplify this, we get 2 pi and 2 pi get cancelled. And that leaves us with just theta multiplied by r. And we often write it the other way around, just because it maybe looks better. It doesn't really matter. Although you can write it like this as well. They're just being multiplied. This is also fine. But you could also write it as r into theta. And that gives you the arc length of the sector. Arc length of a sector is given by this formula now, r theta. And there's a symbol that we use for this, s. S stands for arc length. R is the radius of the sector. And theta is the angle of the sector in radians. So in this case, theta is now supposed to be in radians. So whenever you have an angle given for a sector in radians, you can find the arc length of that sector using this formula, S equals R theta. Okay? S equals R theta. This can be used whenever you have theta in radians. This is the arc length formula now that we would be using. So where did that formula come from? We just understood that. In O levels, we did this formula, theta over 360 into 2 pi r. In radians, it would become theta over 2 pi. And then when we simplify that, we get to this formula, S equals R theta. And this is now what we will be using whenever we have angles given in radians. Okay? So that's one formula that we need to know. Arc length equals radius into theta. Similarly, we had another formula which was area of a sector. What was that given by? Theta over 360 into pi r squared. In this case, theta was supposed to be in degrees. And again, what were we doing in this formula? Pi r squared was the area of this complete circle. Pi r squared was the area of this complete circle. Since we were looking for only this area, the area of the sector, we said, okay, let's just find the proportion of pi r squared that falls in that sector. And how would we do that? We know that the complete circle has an angle of 360 degrees. What's the angle of the sector? That's theta. So we say theta over 360. That's the proportion of pi r squared that we want in that sector. Now, if you were to change the same formula to something in radians, what would that become? It would become theta over 2 pi instead. If theta was supposed to be in radians, now the proportion would be calculated like this, theta over 2 pi multiplied by pi r squared. So the angle is now supposed to be in radians. If the angle is in radians, the formula basically changes to something like this. Theta over 2 pi multiplied by pi r squared. Now let's simplify this. What do we get? Pi and pi get cancelled. What are we left with? We're left with theta over 2 into r squared. We often write it like this. 1 over 2, that's half, into r squared theta. Or you can say r squared theta over 2. Write it either way. That's the area of a sector. And it's written in the formula sheet like this. A equals this. Area of a sector is given by this. And this also has that same condition that the angle needs to be in radians. Theta is supposed to be in radians. So these are the only new things that you have in this topic in circular measure. What? The first thing is you need to understand what radian is and the conversion between degrees and radians. 180 degrees corresponds to pi radians. Then you can use these conversion formulas, multiply the pi over 180 if you have to go to radians, multiply by 180 over pi if you have to go to degrees. Arc length formula, which is S equals R theta, and area of sector formula, which is half R squared theta. Okay. These are now some formulas that you have that you can use to calculate arc lengths, area of sector, perimeter of sector, and anything like that. Okay. So this is the main concept of circular measure. These are all the things that you need to know. But here, we already talked about some basic trigonometry. So in addition to those circular measure concepts, you would need to know how to use sine, cos, and tan ratios in right angle triangles. You would also need to know, if you don't have a right angle triangle, how you can use these sine rules and cosine rules. In addition to this, you would need to know how to find areas of triangles. Remember the formulas that you used to have for that? Finding area of a triangle. There are two formulas that you've done in O-levels. You would need them in this topic as well. So let me quickly remind you about those formulas as well. What is area of a triangle given by? Area of a triangle is given by 1/2 into base into height. That's one formula that you have. Half into base into height. When does this formula work? When you have one side of a triangle given along with perpendicular height to that base. Let me draw a triangle here. If you have a triangle like this and you wanted to use this formula, how would this work? You would say if you are taking this as the base, let's suppose, if you're taking this as the base, what would the height be? Height would be this side, right? If you're taking another side as the base, if you were taking, for instance, the side on the right as the base, I'm sorry, yeah. If you were taking the side on the right side as the base, what would the height be? The height would be perpendicular drawn from that base to the third vertex. So whatever side you're taking as the base, height is going to be what is perpendicular to the base. Now, when you're using this formula, this is one thing that you need to remember. Base here is always one of the sides of the triangle. This is always one of the sides of the triangle. And H is always perpendicular coming from the third vertex. So whatever is not part of the base. So yellow one is the base. What's the third vertex then? The one remaining. The perpendicular coming from the third vertex to the base. Height does not have to be a side from the triangle, but base always has to be a side of the triangle. Okay, so if you're using this formula, you need to remember this. Okay, whichever side you're taking as the base, height is just the side, height is just perpendicular to that coming from the third vertex. Sometimes this can also happen, that you have a triangle that looks like this. You could have something like this. If you had to find the area of this triangle and you were taking this as the base, how would you find the height? From the third vertex, you have to draw a line that is perpendicular to the base. That will go like this. Sometimes the height can also be outside the triangle. That is also possible. In this case, for instance, height is outside the triangle like this. Okay. This is the height. In this case, this is the height. This is the height. And the yellow sides are the bases. Okay. So when can you use this formula? When you have base known, any one of the sides known, and a perpendicular known from the third vertex to that base. Okay. That's one triangle formula that you need to know about. You will need to use this a lot. And then another formula that you need to know about, that's also used a lot, that is half into AB sine C. Half into A into B into sine C. So one formula for area of a triangle is half AB, half into base into height, and the other is half AB sine C. When does this formula work? This works for any triangle in which you are given two sides, or you know some, or you can somehow calculate two sides, and you know the angle between those two sides. So for instance, if you have a triangle like this, in which this is A, this is B, this is C, the side opposite to A would be small a, side opposite to B would be small b, and the side opposite to C would be small c. If you know any of the two sides, let's say A and B, and the angle between those two sides, that's this angle, you can use this formula. Okay, so what you need to remember about this formula is C is the angle between the sides A and B. So if that condition is met, you can use this formula. So if you have two sides given and the angle between those two sides given, you can use this triangle formula to calculate the area. Okay, so you will be doing this a lot in this topic as well. When you have mensuration questions, we'll have some sectors, and sometimes have some triangles there as well. So in order to find the area of the triangle, you would need to use this formula as well. So there are two triangle formulas that you need to remember then. One is half into base into height. Okay. In that case, you need to know one side and perpendicular from the third vertex to that side. If you know that, if you have that information, you can use this formula. If not, this is the alternative. You can use this formula when you have two sides known and the angle between those two sides known. This is the other formula that you can use. Okay. Now, once you understand these two triangle formulas, you will see another shape sometimes given as well, and that looks like this. You could have a sector like this. You could have a sector like this, and in that sector, you've got this triangle. So this whole thing is a sector. So you need to understand the terminology as well. This whole thing, the yellow thing, is a sector. Inside this sector, you've got this triangle. And you're left with this area here. This area is called a segment. This whole shape, the outer boundary, that is known as a sector of a circle, right? It always has a center, two sides are radii, and the third side is an arc. So in a sector, you have three sides, two radii and one arc. In a sector, you have these three sides. In a segment, you only have two sides. One is a chord in that sector, and the other is an arc, this arc in that sector. So this is a segment. You need to understand this terminology. This is called a segment. How do you find area of a segment? If you know that this is R, and this is theta. You need to know this as well. Area of a segment. How is this calculated? Now, you could kind of remember a direct formula for this, but let's understand first where that comes from. And you can just use that as well, as in, if you want the area of this green part, what you can do is you can say the area of that part is going to be the same as area of the sector minus the area of the triangle, right? So if you find the area of this whole thing, of this whole figure, which is a sector, and subtract from that the area of this triangle, you would get the area of that green part, right? Now, how can we do this? Area of sector, what is that given by? We just did that here. Area of a sector is given by half r square theta. That's the area of the sector, okay? So we can just use that here. We can say area of sector is equal to half r square theta. Subtract from that area of the triangle. What's the area of the triangle now? We have two sides given, r, and we have the angle between those two sides, that's theta. we can use this formula that we just did, half AB sine C. What is this going to become? Half into R into R, that's R into R, into sine of the angle between them, which is theta. If we were to simplify this, we get half R squared theta minus half R squared sine theta. And if we take half R squared common, that leaves us with half R squared into theta minus sine theta. This is the formula for area of a segment, where theta is the angle of the sector and R is the radius of that sector. This formula can give you the area of the segment directly. Now, it's not necessary for you to remember this, however, because you just calculate these areas separately, find the area of the sector, find the area of the triangle, and then just subtract those two. But in the marking scheme, sometimes you'll see this being used as well. So you need to understand that this is just coming from this. Now, it's your choice if you want to do these separately like this, or if you want to use this formula directly, you can do that. But if you use this formula directly, or even if you do this, because you have area of sector here, you need to remember theta is in radians. Theta is supposed to be in radians here. Theta cannot be in degrees here. Is that okay? So what have we done then? Area of a sector, arc length of a sector, area of triangle, the two formulas that we have here, area of a segment. This is how we calculate this. Okay. Now, when you're doing all of these calculations, you will have angles given in radians. Okay. Angles will not be given in degrees. The angles are going to be in radians. If you look at your calculator, if you look at the screen of your calculator, on top, you generally have D written like this. Okay. That basically stands for degrees. Your calculator is in degrees mode. So if you were to calculate, for instance, sine of 45, your calculator is going to give you square root of 2 over 2, because that's the value of sine of 45. Okay, you can try that. Sine of 45, that gives you square root of 2 over 2. Now, what is 45 degrees in radians? 45 degrees in radians is pi over 4. Right? Pi over 4 is what 45 degrees is. Why? Because 180 degrees is pi. So what should be 45 degrees? 45 degrees is 1/4 of 180. So that's pi over 4. Now, if you were to try this on your calculator now, sine of pi over 4, what does your calculator give on this? Sine of pi, sine of pi divided by 4. That's giving me 0.0137 something, which is not the same as this. Square root of 2 divided by 2 was actually 0.707. When I do this, I get a different answer. The reason for that is your calculator is understanding pi over 4 as an angle in degrees, because calculator does not know whether the number that you're inputting here is in degrees or radians. Since the calculator is in degrees, calculations in radians, what you have to do is you have to change your calculator mode. Okay, so throughout your A levels now, you will sometimes be using degrees, you will sometimes be using radians. So whenever you're doing a calculation, make it a habit that you always look on the top of the screen and see whether you have D written there or R written there. When your calculator is in radian mode, you have R written on the screen. When your calculator is in degrees mode, you have D written on the screen. So whenever you do any calculation involving any angles, always look at the top and see whether you have D there or R there, and if that's appropriate to what you're doing. If your angles are in degrees, it should be in degrees mode. If your angles are in radians, it should be in radian mode. Now, how do you do that shift on your calculator. It depends on the version that you've got. So in the version that I have on my hands right now, this is ClassWiz. You have to go to setup. In setup, you find number format. So it's this calculator, ClassWiz. On this, what you do is you go to setup. How do you go to setup? You press shift and then press the menu button. You have setup button on that as well. In setup, at number 2, you have angle unit. So when you press 2, you get 3 options there: degrees, radians, and gradient. Gradient is another unit that you don't need to know about at this point. You already know about degrees. If you want to convert your calculator to radian mode, you have to press 2 there to convert it to radian. Once that conversion is done, you should see R written on top. And that means your calculator is in radian mode now. And once you're done with that, you would see, if you do the same calculation now, sine of pi over 4, it should now result in under root 2 over 2. But now sine 45 would not give you under root 2 over 2 because your calculator would assume 45 to be in radian mode. So whatever calculation you're doing, you have to make sure your calculator is in the right mode. If you're using an angle in degrees, your calculator should be in degrees mode. If you're using an angle in radians, your calculator should be in radian mode. So be very careful about this. In this whole topic, circular measure, whenever you're doing a calculation, your calculator needs to be in radian mode because you'll always have angles given in radian mode. You will have this inclination of converting everything to degrees when you're doing the first few questions because you're used to using degrees, but please don't do that. Work with radians because in paper 3, you would realize almost every topic requires you to use radians. You can't use degrees at all. So you need to get used to using radians. And in circular measure, the angles given are going to be all in radians. If you keep converting back and forth to degrees and then radians, it will waste a lot of time. You can't afford to do that in the exam. Sometimes the exams are lengthy and that will waste a lot of time. Okay, so you should not be doing any conversions. Work with the unit that is given in the question. If they're using degrees, use degrees. If they're using radians, use radians. Just make sure that your calculator is in the correct mode. Okay, so that's how you do this conversion between degrees and radians on your calculator. Make sure that you're using the correct mode there. Now, what you will be doing over the next 2 days now, I'll be uploading this worksheet on circular measure. Let me just show you some questions from this worksheet quickly so that you understand what we have done is going to be enough to do all questions from this worksheet. I'll just do a small thing quickly before we end. And then you should be able to do all of this. See, you have questions like these. You have a triangle, and inside that triangle, you've got a sector. You want to find the shaded area. How would you do that? It's simple mensuration question. You find the area of the triangle, subtract the area of the sector from that, and you would get the shaded area. Okay. Now, you know how to find the area of a triangle. You have 2 formulas for that. You know how to find area of a sector. You know half r square theta. Just find the 2 areas and subtract the 2. Right? Pretty straightforward. You have done the same thing in O levels. The only difference was that you used to do that in degrees. Now the angle is in radian. So you'll just be using different formulas for this. Okay. The second part is find the perimeter of the shaded region. What's perimeter? Perimeter is just the length, the total length of the boundary of the shape, right? So the shaded region is this. What's the boundary of the shape? It's this part, this arc. So we'll just find this arc length. What's the formula for arc length? S equals r theta. You'll have this length. This is 4 given already. You have this length. This is also given already. And then the last length is CD. How do you find this length CD now? You have a triangle in which you have 2 sides known. You have 2 sides known. And this side is given. This side is given. You have the angle between them as well. You can find the third side from that. You can use cosine rule if you want. You could also make it an isosceles triangle like this by dividing it into two parts. In fact, this is an isosceles triangle. So what you can do is you can divide the triangle into two parts like this, make it a right angle triangle. The angle also gets divided. This is 0.4. You can use sine, cos, tan ratios as well to figure out this length as well. So try doing this. These are questions that are very similar to what you've done in O-levels, only the angle unit has changed, okay? But there's one thing that you'll find in these questions, and that will be that they will often be asking you to find an exact answer. So for instance, if you look at this question here, question number, I would say exact anywhere here. Yeah, so for instance here, part 1 here, it says, show that the exact length of AX is 6 under root 3 exact length. So they'll often be asking you for exact answers. Sometimes they'll say they want an exact answer, or they might just say something like this, that your answer needs to be in terms of pi and square root of something. Here as well, for instance, they're saying your answer needs to be in this form, a under root 3 minus b pi. So in terms of pi and under root 3. So they will often be asking you for exact answers, okay? Now, how would you get those exact answers? Because you would have, when you're using triangle formulas, for instance, you have half AB sine of theta. Sine of theta is often in decimals, but there are some angles for which you get an exact answer as well. So that's what I want to talk about before we end. And that is, there are some angles for which you would need to use exact values in the exam. Exact values of sine, cos, and tan of some common angles. So the examiner is going to require exact answers when you're dealing with some of these angles. Now, what are these angles? In degrees, they are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. In radians, these same angles
Sir?
would be, yes?
Sir, is it always important to learn these values? Because मैं हमेशा
No.
jumble up करती हूँ.
No, you don't have to memorize these. You just need to know that if you have one of these angles, you have to use exact value sometimes. You can find that exact value from your calculator. It's not necessary to memorize these values, but you just need to make sure that you remember, if you have one of these angles, you should be using an exact value if the question says that, okay?
Okay, thank you.
Now, I'll show you how to do that. So in radians, these values would be 0, pi over 6, pi over 4, pi over 3, and pi over 2. You need to use exact values of sine, cos, and tan of these angles. Now, in our time, we used to have to memorize these values because the older calculators, they did not used to give exact values of these, okay? So if one of you has an old calculator, you might know that you don't get exact values when you find sine, cos, or tan of these angles. They give you values in decimals, and Cambridge expected us to memorize these values. But they still expect you to use exact values for the sine, cos, and tan of these angles. However, since the new versions of calculators, they give you these exact values, you can just use these values from the calculator. Just have to make sure that you don't write this value in decimals. That's all that you've got to do. And you also show working. I'll explain what I mean by that. Let me first write down these values. So sine of 0, what's that? It's 0. Sine of 30 degrees or pi over 6, that's 1 over 2. Then you have under root 2 over 2. And then you have under root 3 over 2 and 1. Cos is just the same numbers in opposite order. So that's 1 under root 3 over 2. And you have under root 2 over 2. You have 1 over 2 and 0. Tan, as you would learn in trigonometry, tan is sine over cos. So you can just divide the two. That's 0. And this is under root 3 over 3. Then the next one is going to be 1. And this is under root 3. And this is undefined. Now, these are some common angles. Whenever these are used in the question and they want an exact answer from you at the end, you are going to use these values. So for instance, if you have to calculate area of this triangle, so I have this triangle and I know that this angle here, for instance, I know that this angle is, let's say, 60 degrees. Okay. And I know that this side is 7 centimeters and this side is maybe 9 centimeters. And they want us to find the exact area of this triangle. How would we do that? We would say area of triangle is given by half into AB sine C. Remember, that's the formula that we can use here. Input values in this. That gives us 1 over 2 into A, which is 7, into B, which could be 9, into sine of this angle. Let's actually use this in radians because you will have values given in radians here. 60 degrees in radians would be pi over 3. So let's say they have pi over 3 given here. You'd say sine of pi over 3. Now make sure your calculator is in radian mode here. That's important. Now, since you want an exact area of this triangle, you are not going to use a decimal value for this. Sine pi over 3, you would need an exact value for this. What's the exact value of sine pi over 3? The exact value of sine pi over 3, if you look at this table, sine pi over 3, it's under root 3 over 2. Now, you don't need to memorize this. All you need to do is make sure your calculator is in radian mode for this. Once you're done with that, you do sine of pi over 3 on your calculator, and your calculator should give you under root 3 over 2. Okay? The only thing you need to do is just don't write down the final answer here directly. Don't write down the final answer. Show working for this. What I mean by that is input sine pi over 3 here first. Input sine pi over 3. The value that your calculator is giving you is under root 3 over 2. Show this value here first. Show one step in which you write down what the value of sine pi over 3 is. Okay, you have to show this. Once you're done with that, then you can write down the final answer. So multiply under root 3 over 2 by 7 and 9, divide that by 2. Your calculator gives you the direct answer for this as well, 63 under root 3 over 4. All you need to do is make sure that you are showing this step, that sine pi over 3 evaluates to under root 3 over 2. You have to show that. Don't jump from this step to this step directly, because your calculator can actually give you this answer directly as well, to 63 under root 3 over 4. The examiner just expects that you show this working. That instead of sine pi over 3, you first write under root 3 over 2, that this is what it evaluates to in exact form. And then after that, you can write down the next result. Okay, this step is important. That's the only thing that's required from you. These are the values. These are the angles for which you need to use exact numbers. If you have any one of these angles, if you're finding sine, cos, or tan of them, you have to write down the exact value here like this first, and then you can write down the final answer after that. Okay, just make sure that you follow this rule and then you'll be fine. Okay, so these are all the concepts that we need to know in this topic, circular measure. In the next class, we will quickly review angle properties of circles. You have done those in O levels as well, right? Angle properties of circle, right? For example, diameter makes 90 degrees with the circumference, and angle at the center is twice the angle at the circumference, and the other properties like that, because sometimes you need to use some of those in these questions as well. But you've done those in O-levels already, so you should be able to do all questions from the worksheet once you understand these concepts. So I expect you now to attempt those questions. I'll be uploading this worksheet today. You'll have some questions assigned from that. Please try to do as many of those questions as you can before the next class, because now on Thursday, we will be doing practice of this topic. I'm sorry, I started with trigonometry. I wanted to do that today, but in the middle, I realized that we would not be able to do much in today's class. As far as the worksheet questions are concerned, you would not have been able to do anything from the trigonometry worksheet after that. I thought the next 2 days would be wasted then. So please make sure that you don't waste them now, because now you have all of these concepts covered for at least circular measure topics. So you can attempt all of those questions now. So make use of this time, the 2 days that you have now. Our next class is on Thursday. Before Thursday, I want you to have attempted at least 7-8 questions from the worksheet. Okay, at least 7-8 questions, please. Okay, so what have we done? We revised this trigonometry today. We talked about radian. We did this arc length formula, S equals R theta. We did this area of sector formula, half R squared theta. Area of triangle formulas, half into base into height, half AB sine C. Area of segment, how do we calculate area of segment? Sector minus triangle. Exact values of sine, cos, and tan for these common angles. We need to use these sometimes. You can use a calculator for this, but just make sure that you show complete work. Okay. So now, please try at least 7-8 questions from the worksheet on Thursday. We will be discussing if you have any problems from those questions. All right. Any quick questions if you have any? Otherwise, I'm going to end today. Any problems, anyone?
No, sir.
No questions? Okay, so that was a short topic. So that's good that you've covered this then, at least in terms of concepts. We will be spending time on some practice questions. I'll actually upload it right now, so you don't have an excuse later that you could not get time to attempt these questions. You have like 48 hours now before our next class. So please try to do it in this time, at least 7 or 8 questions. Okay, I'll upload it right now, right after the class. I'll see you again on Thursday then. Allah Hafiz.